Okay, today we're going to talk about waves. Waves are really super important. You're probably familiar with a lot of things where waves show up. Waves on the ocean, sound waves. But it turns out they probably show up in places you didn't even consider. For example, light is a wave. So to really understand optics, and when we do the optics section in this class, you're really going to need to understand waves really well. You're going to need to understand sine waves really well. When we talk about modern physics, we'll find that everything is a wave. Electrons, protons, dogs, cats, apple pies, they all behave like waves, and so it's essential that you understand waves really well. So pay really close attention today. In this presentation, we're going to show the basics of waves and talk about a lot of the notation and terminology we use with waves. All right, first of all, what are waves? Where do they come from? Well, a wave is the propagation of energy through some medium. So the medium doesn't travel very far, but the energy travels across the medium for long distances. In order to have a wave, we need a restoring force, so that if I take some piece of my medium and I displace it, there's some force trying to push it back. And then there's coupling that takes that motion of one piece and moves it to other pieces, and then I need inertia. Alright, so for example, waves on a string. The thing that's moving, of course, is the string. Right? But if there were no wave coming through, my string would just be flat. If you look at this little piece right here, it's displaced. There's a restoring force. There's the tension of the string on either side pulling it down. Alright, so if you look at this little piece right here, there's a big force this way and a big force this way, but there's also a downward component of force due to the string on either sides of this little slice of string. The horizontal components mostly cancel out, but the downward components add together, so I pull the string up and there's a restoring force trying to pull it down. Alright? There's coupling to the other pieces. They're interacting with one another, and there's inertia. So as this piece comes down, when it gets to the bottom, it's not just going to stop, it's going to keep moving. Right? And this is everything you need to set up a wave. Now, in a string, you can find the velocity that the waves travel on a string, and the equation the book gives you is the square root of tension over mu, where mu is the linear mass density. It's the mass per unit length. So when we talked about density before with fluids, it was always mass per unit volume, but when we talk about strings, we very often talk about the linear mass density. It's just the mass of our string divided by how long it is, or the mass of a segment of the string divided by the length of that segment. Alright, where does that velocity come from? The book does a hand-waving explanation, but it's really just a hand-waving explanation. They present it almost like it's a derivation, and it may be kind of confusing, and that's because it really is just some hand-waving. The right way to do it is to find the wave equation that describes a string and solve it. Unfortunately, we don't have the tools to do that in this class. Now, there's two general types of waves, what we call longitudinal and transverse waves. Alright? A transverse wave is the easiest one to draw. So a transverse wave is like what we have on a string. Alright? So here's my string. Here's the string with no wave going through. Alright? So x, I'm going to label each piece of my string with some distance x from some reference, one end of the string maybe. Alright? So x tells me which piece of the string, and y tells me how far that piece of the string is from its equilibrium position, from where it is when no wave is going through it. So this could be a wave on a string, or maybe I have a slinky and I'm shaking it back and forth. Alright, whenever I have a transverse wave, I can describe the displacement, y, as a function of x and time. Alright? A longitudinal wave is what you would get if you took a slinky and instead of waving it back and forth, what if you shook it this way? So here's my slinky, and maybe parts of the slinky are bunched up, parts are stretched out, parts are bunched up, right? And so I have a compression wave. A longitudinal wave is a compression wave. This is what you get when you shake the end of a slinky back and forth. It's also the kind of wave that sound waves are. Sound wave is a compression of the air. You talk, your mouth, your voice compresses the air, and that compression, you put energy into that compression, and that energy travels. The compression wave travels through the air. Alright? Now, when we describe longitudinal waves, things can get a little sticky. So let me take a minute and describe what we're doing here, how the notation works. So imagine, if you will, I have my slinky, or I have my piece of air, or whatever this longitudinal wave is going to travel through. And let's imagine there are no waves going through. It's in equilibrium. Everything is sitting still. At this point, I come in and I label the different pieces of my medium. All right? And so this may be over here, let's see, that's about 3 centimeters. So this piece right here, it has a label of x equals 3 centimeters. All right? That is a label. It tells me about what part of the slinky, or what part of the air I'm looking at. Now imagine I have a compression wave coming through, and the slinky gets compressed or whatever, and this piece moves over here. All right? So initially it was 3 centimeters from the end. Now let's say now it's like 1.5 centimeters from the end. What is x for this piece? It turns out x is still 3 centimeters. X does not tell you where the piece of the slinky or the piece of the air is at any given time. It tells you what it is when it's in equilibrium. So this will always be the x equals 3 piece of the slinky. If I come and put a marker on right here at the 3 centimeter point, as this piece wiggles back and forth as waves go through, it will always be the 3 centimeter piece. So this piece right here, it's got the marker on there, so I know this is the 3 centimeter piece, even though it's only 1.5 centimeters from the end. All right, so x is a measure, it's a label for a piece of your wave medium, of your slinky or your air or whatever this longitudinal wave is going through. All right? Then we have another term, which is the displacement. It says how far you have moved from your equilibrium position. And so I could describe the wave as a displacement s as a function of x and time. Now, at this particular time, if I plug in x equals 3 centimeters, this piece is over here. So what is the displacement? It's moved to the left by 1.5 centimeters. So s would equal negative 1.5 centimeters. All right? Okay. Now, traveling waves. How do waves travel? In this class, we're only going to talk about a type of wave known as, or a type of medium known as a dispersion-free medium. In a dispersion-free medium, all waves travel at the same velocity, and all waves travel rigidly without dispersion. In other words, if I have a wave that's shaped like this at some time t equals 0, sometime later, the wave will have exactly the same shape. It just will be moving. Now, I could have two waves going in opposite directions, and as they add together, I can have the shape of my string change. All right? But the idea is I generate a wave traveling in some direction. It will travel rigidly. How can I turn a shape then into a traveling wave? So for example, I have this shape right here, which is just y is equal to e to the negative x squared. All right? Now that's not a very good wave because it doesn't have any units, right? If this is a wave on a string, y ought to have units, say, of meters, but there's no units here. So I could maybe add some constant here with units of meters. My exponential, I only take exponentials of unitless things, right? And x is going to have units of meters, so maybe I divide by some x naught squared or whatever. All right, the point is the computer doesn't care about units, and so this is something I'm plotting on the computer. All right? So anyway, I have some wave, and maybe at some time it's described by some function f of x. How do I turn that into a function of x and time that describes that wave traveling to the right or traveling to the left? Well, it turns out what we do is we just say, well, look, if I want to translate a shape, all I have to do, f of x minus x naught, that will translate my function by a distance x naught to the right, right? So if I take this function right here and I plug in, I change it to y is equal to e to the negative x minus x naught squared, right? I replace x with x naught. If I plug in 0 for x, I'm not taking e at 0 anymore. I'm taking it over here, right? So I look at 0, but I get this piece of the wave right here, all right? If I look over at x equals x naught, the argument here turns to 0. So the top of this wave has moved over to x naught, right? So by doing this substitution, I've moved my whole plot over to the right by an amount x naught. Okay? So the idea, the way I make a rigid structure into a traveling wave is I just replace x with x minus how far the wave has moved, and that's going to be a function of time, right? My wave is traveling at some velocity, so I just replace x with x minus vt, and that will make a wave going to the right. If I want my wave to travel to the left, I just take x plus vt, and that will make a wave traveling to the left. Alright, so here's an example. We're going to take this wave right here, and I'm going to take this expression, I'm going to replace x with x minus vt, and plot that on the computer and see what happens. There it is. Alright? So if I replace x, if I replace x with x minus vt, I get a wave traveling in the plus x direction. If I replace it with x plus vt, I get a wave traveling in the minus x direction. Alright, sine waves are essential. Alright, sine waves are important because harmonic oscillators oscillate sinusoidally. Right? You remember from Physics 121, if you have a mass on a spring, it oscillates sinusoidally. If you have a pendulum that's oscillating at small amplitude, it oscillates roughly sinusoidally. Alright? If I have some complicated thing like a wine glass that I'm trying to break with my singing, it has certain modes of oscillation that all oscillate sinusoidally. Alright? So it's really important to understand sine waves. Also, when we deal with more complicated waves, it turns out you can write any wave as a sum of sine waves. So if I understand what sine waves do, I can probably figure out what other waves do too. So a sine wave, if I plot a sine, it looks something like this. So let's understand some of the terminology of our sine wave. Okay, first of all, if I have some sine wave, a sine kx, how do I turn that into a wave? I just replace x with x minus vt, right? We also usually like to write it this way, alright? So all we've done here to go from here to here is we've taken the k and we've multiplied through. So we have k times x, and then we've defined this thing omega to be equal to k times v. Alright? Okay. So omega is just k times v times t. Alright? Now, what does it all mean? Okay, when we talk about waves, sometimes we talk about the amplitude of the wave. The amplitude is this distance right here, from 0 up to the maximum height of our sine wave, or the distance down to the minimum, either way. So it's not the full peak-to-peak distance, it's from 0 up to the maximum excursion. That's the amplitude, and that's a right here in this equation. Alright? We also have the thing we call the wavelength, and the wavelength is how far I have to go before the wave repeats itself. So I'll take my wave, I'll freeze it in time. Right? This wave is frozen in time. It's really moving, but I've taken a snapshot. Alright? That distance right there is the wavelength, and we usually represent that with the Greek letter lambda. Alright? So it's the distance from valley to valley, or from peak to peak, or from crossing zero as we go up till the next crossing zero as we go up. Any point to the next point where the wave is doing the same thing again. It's how far in space we have to go to repeat the wave, and we represent that with the Greek letter lambda. K is up here. You see K right here and here. K is what we call the wave number, and the wave number is just 2 pi divided by the wavelength. Alright? It basically says, how far does x have to go before my sine wave repeats? Well, a sine wave repeats every 2 pi radians. So if I change x by 1 wavelength, the phase of our sine wave, the phase is just the thing we plug into our sine wave, the total argument. If I change x by 1 wavelength, the phase of my sine wave should change by 2 pi radians. So therefore, you see k is just 2 pi over lambda. If I multiply k times lambda, I'm going to get 2 pi radians, and that's what makes my wave repeat. Alright, so k is the wave number. It's the number of radians per meter. So as I'm moving along my wave, every meter that I move will change the phase of my sine wave, the argument of my sine wave, by k. Alright? It's the number of radians per meter. Alright, now in time, now imagine I've got my wave, and let's let my wave be going through, but I'm going to freeze space and look at time. So I'm going to look at my wave as it passes through this point. Alright? And it's going to be going up and down. Alright? The period is the time it takes before it starts to repeat itself. So I watch this wave in time, and I see it's repeating itself over and over again. T is the period, which is the time I have to wait before it does the same thing again. All right? If I take 1 over the period, I get the frequency. So if the period of my wave is 1 second, the frequency is 1 inverse second, or 1 hertz. An inverse second is also known as a hertz. If the period is 2 seconds, the frequency then is going to be half a hertz. If the period is half a second, it takes half a second for the wave to repeat, then the frequency is 1 over half a second, or 2 hertz, or 2 cycles per second. All right, so the frequency is how many times the wave repeats every second. All right, there's also this thing we call the angular frequency. We use a lowercase Greek omega to represent it, and that's just 2 pi over the period, or 2 pi times the frequency, right? Same thing. The angular frequency is kind of like the wave number, but in time instead of space. It's the number of radians of phase that happen per second. So the wave number, k, is how many radians as I move in space, freezing time, and the angular frequency is the number of radians per second in time when I freeze space, when I look at just one point on the wave. All right? So it takes 1 cycle to do 1 cycle, so the frequency is in cycles per second, but it takes 2 pi radians to do 1 cycle. The angular frequency, omega, is in terms of radians per second. All right, now, there's all kinds of relationships between the wavelength and the frequency. If I know the wavelength of a sine wave, I can find the wave number, right? If I know the wavelength, I know that the wave number is just 2 pi over the wavelength, right? So if I know the wavelength, I can find the wave number. That's a lambda there. But there's also a relationship between the time and the space parameters. If I know the wavelength, I also know the frequency, right? Because they're related to each other. How are they related? There's all kinds of relationships you can come up with. The one that's easiest to remember, I think, even though it may not be the most useful one, is just to remember that the velocity that our waves travel, they travel 1 wavelength per period, right? That ought to be pretty easy to remember. All the other ones that come up more often can be derived from that. All right, just remember your sine wave is going to travel 1 wavelength every period. Well, I know that, for example, the wavelength, if I solve this, it's just 2 pi over the wave number, right? And I know that the period is 1 over the frequency, and the frequency is angular frequency over 2 pi, so I can plug that in, and I can find then that the period is just going to be 2 pi over omega. So I can plug that in, and I can find that the velocity of my wave is 2 pi over k divided by 2 pi over omega. 2 pi's cancel, and this just ends up being omega over k. That's the velocity. Right? There's another relationship that shows up in your book. Like I say, the easy one to remember is the velocity of a wave is 1 wavelength per period, the velocity of a sine wave, I should say. And remember that the velocity is fixed for the medium. It depends on the medium, not on the wave. And so it's just a constant. So if I have the wavelength, I can find the period. If I know the angular frequency, I can find the wave number. If I know the spatial characteristic of my sine wave, I can find the time characteristic. And you can come up with all kinds of relationships here. Now, the speed of waves on a string. How do we derive it? I mentioned that your book does a, quote, derivation, but it's really more hand-waving, and I find it kind of confusing. The right way to do this is to write down the equation that describes waves on your string, and then solve it and see what the velocity is. Now, what is the equation? It turns out that the equation is what we call the one-dimensional linear wave equation, and it looks like this. The second derivative of y with respect to time is equal to the second derivative of y with respect to x, and then you put the speed of the wave here squared. I always forget what side to put it on, but I can use units, right? This has units of meters per second squared. This has meters per meter squared. This is meters per second squared, so I need to cancel out a 1 over meters squared here and add in a 1 over second squared. So the units work out if I put it on that side. Anyway, enough rambling. That's the equation. How do you solve that equation to find what v is equal to? Well, you don't really solve it. What you do is you derive this equation. You look at your string and you say, you know, how does this string behave? And what equation does it follow? You come up with that equation, it looks like this, and whatever's sitting right there is the velocity squared. We don't have the tools to do that in this class. This is what's known as a partial differential equation. You may see them someday if you take math classes. If you take Physics 318, you'll see them. The point is, this is beyond what we normally do in this class, so I don't expect you to be able to come up with this equation. Therefore, I don't expect you to be able to derive the velocity of waves on a string. So for now, you're just going to have to take it on trust that it's this. All right? It's unfortunate, though, that we don't have the tools or the time to derive this equation, because derivations, first of all, help us really understand the medium. If we could derive this, we would understand much better how waves propagate on a string. Also, in the process of doing the derivation, you make some assumptions. And without knowing those assumptions, we don't know when all of the stuff we're talking about is true. And it turns out that the main assumption that you make when you derive this equation is that your waves have a small amplitude. All right? If your waves start to have a big amplitude, this equation's no good, and it turns out things that we're going to talk about in this class won't necessarily be true. All right, now sound waves. We talked about waves on a string. Sound waves, so waves on a string are transverse. I mentioned before that sound waves are longitudinal waves. So you've got this air, and you push a little piece of air this way, it squishes the air up, and then it's all tense, it's got a higher pressure, and it tries to push back, which pushes on the next piece, and this pressure wave can propagate, this longitudinal wave can propagate. Now the individual pieces of air, they just wiggle back and forth a little bit, but the power goes a long distance. So you can sit at the back of the classroom and you can hear my voice, but you don't smell my breath. The molecules directly in front of my mouth don't get to you, but the power, the wave, does. Now the speed of sound, it turns out, is very analogous to the speed of waves on a string. All right? On a string, we have something that tells us about the restoring force on the top, and then we have the linear mass density. For waves on a string, it turns out that the restoring force is due to the bulk modulus of the material, whether it's air or water or steel. It's how hard it is to compress it, right? I squish it, how hard does it push back? So the bulk modulus is here, and then instead of the linear mass density, we have just the density. All right? Sound waves tend to be three-dimensional, unlike guitar strings. So the speed of sound is just the bulk modulus over the density, and then take the square root of that. All right? Turns out you can sort of guess this by knowing you need to have some springy thing, you need to have some density thing, and then trying to make the units work out. You can actually come up with this. You might think about that. Review what bulk modulus is from your Physics 121 textbook, and then see if you could kind of make a guess at what the velocity might be. This is what's known as dimensional analysis, just trying to make the units work. All right? Okay, the velocity of sound in air at 20 degrees C is 343 meters per second. What does that mean? It means if I have a sound wave with a wavelength of 1 meter, it has to oscillate at a frequency of 343 hertz, right? Now, so imagine I have an organ pipe that has a certain, because of its shape, it has a resonance with a wavelength of 1 meter. I play that organ pipe, it's going to generate a frequency of 343 hertz. Helium is lighter than air, but it turns out the bulk modulus only depends on the pressure, pretty much. So helium at atmospheric pressure, it's going to have, what's going to happen to the velocity? The velocity of sound waves is bulk modulus over density, and I'm claiming here that the bulk modulus mainly depends on pressure, so the bulk modulus for helium at atmospheric pressure ought to be pretty much the same, but the density is going to be lower. So what's going to happen to the velocity? The velocity of sound in helium is going to be much faster than in air, all right? So imagine I take that same organ pipe and I make it ring, all right? And it generates a wavelength of 1 meter, the frequency will be higher. That's why you hear a higher pitch. When you inhale helium from a balloon and speak, your voice goes up in frequency. That's why, because the speed of the helium is faster than the speed in air at the same pressure. Now, sound tends to travel faster sound tends to travel faster in liquids and solids than in air. That's because the molecules are closer together, all right? So, for example, In water, the speed of sound is 1,490 meters per second compared to air. All right? So if you look at this, velocity is the square root of the bulk modulus over the density. Right? The density of water is a lot higher than air. The molecules are packed a lot closer together than air molecules are in air. All right? But in air, it's really easy to squish these molecules together. But in water, the molecules are already touching, and it takes a lot of pressure to squish them together. So although the density is much higher for water, the bulk modulus is much, much higher. And as a result, the velocity of sound in water is much higher than the velocity of sound in air. When you go into a solid, it's a similar tale, right? That the bulk modulus gets really, really big. The density of aluminum is much bigger than the density of air. But once again, the bulk modulus is really big. In a solid, it's really hard to squish things together. Now you should go do a cool experiment, all right? You can take a break, pause the video, and go and make yourself a milkshake. And when you do that, you want to do it this way, okay? So you're going to have your blender. You're going to whip up your milkshake. What is your milkshake? It's mostly water, right? So take a rigid glass, like a tall glass cup, put water in it, tap on the bottom. See what pitch it makes. It'll make a really high pitch because the velocity of sound in water is really quite high, all right? Then dump the water out and pour your milkshake in and tap the bottom. What will happen? All right, the density of your milkshake is comparable to that of water. It's water basically with some other stuff in it. But some of that stuff in your milkshake are little bubbles of air. All right, those little bubbles of air don't change the density, by orders of magnitude, right? It's still mostly just water. But those little bubbles of air make it really a lot easier to compress the fluid, because when you compress the fluid, you don't have to compress the water, you can just compress the little bubbles of air. So your milkshake is going to have a bulk modulus, which is kind of on the order of magnitude of air, but a density on the order of magnitude of water. You put those two together and you get a really low velocity of sound, and your milkshake will make a really deep tone. All right, go do that now, and then come back. Okay, why do we not hear collisions and explosions from outer space? In a vacuum, there are no molecules. A sound wave is this air, these little bits of air pushing on each other, these molecules bumping into each other. Without those molecules, sound cannot propagate. So without molecules, we cannot have a pressure wave. Sound cannot travel in a vacuum. Now, the intensity of sound, what is the intensity? Intensity, whether we're talking about sound or light or whatever, intensity is power per unit area. All right? So if I have some sound wave coming through and just a bit of it hits my ear, the power that hits my ear is going to be the intensity of the wave coming in times the area it hits. So it's a way to talk about how the power coming from some source is spread out in space. And the intensity depends, you look at the equation, it depends on the power as well as the distance from the source. Why is that? Why would it depend on the distance from the source? Well, intensity is power per unit area, right? And imagine if I have a little speaker here that's giving off waves. As you move further and further away, that sound gets spread over a bigger and a bigger area. So imagine that the sound coming out of my speaker is going out and spreading over little shells that are a piece of a sphere. How does the surface area of a sphere change with radius? The surface area of a sphere is 4 pi r squared. All right, so if I have a source that's emitting spherical waves, emitting waves equally in all directions, the intensity is just the power it emits divided by 4 pi r squared, where r is the distance from the source to where you're measuring the intensity. In general, the intensity, even if the waves don't go out perfectly spherically, in general the intensity is proportional to the power over r squared. All right? And that's the end of our presentation.